Okay, thanks. Yeah. Here, as I was showing you, that the straight line represents the hyperplane, and this hyperplane is written in an input space where the input feature vector is represented by y. So W transpose y, and this no, W transpose y equal to, if I say 0, which means then the hyperplane should have been passing through the origin, and one half of the one half of this hyperplane would be positive half, and we are transforming input in such a way that all the input samples, they belong to the positive half, because what we are doing, the input samples which are supposed to be present in this in this half, that means if I consider x and x prime, these are the two representative feature vectors of the input data. So if the sample is in the negative half, we are simply negating it. That means we are considering a transformation, and that is shown here y prime, so which is simply the inversion of x prime, and that's how it goes to the other half, positive half. And whereas the input sample in the positive half, they remains as it is. And apart from that, to introduce the linearity operations, what we did also an augmentation of an additional dimension. So if I consider that actual input sample, what is given to you like x tilde with say d-dimensional space, and in a d-dimensional space, and some level will be there, either +1 or -1, whatever. So this is the way the training data will be given to you. Now, but when you convert it to a input vector or feature vector augmenting an additional dimension, then we simply append one more field with the vector in the column vector, and but the value would be always 1. So in that case, we can simply write the form of the linear function, which was actually something like this: a W transpose x plus say W naught. This was the functional form, linear functional form. But to make it, I should say here x tilde, if x tilde is the input, and said this W is W tilde to transpose. So this is the functional form of the original data what is been given to you. To make it a linear operations like W transpose x, what we did, we simply augment x with this additional dimension, and then W becomes W tilde, and with an appended of an additional dimension is W naught. I hope this part was clear to you, and that's why the problem of the classification is that we are trying to get that hyperplane which is passing through origin, but all the normalized sample should lie in its positive half. So it makes your error definition very simple. In that case, if I say that if W transpose y is less than 0, suppose you have taken some hyperplane where W transpose y is less than 0, which means this is the case of misclassification. And in your error measure, we are simply adding them. So one of the simplest error measure is that that is what is called perceptron error measure. We are simply adding this deviation from towards the negative half from the I should say from the hyperplane. In a simplistic way, this measure is there. So this value itself, this scalar value itself, we are considering, and that gives you the corresponding error value. That part we discussed in the previous class. And then this is one simple form of error, which was called the perceptron error. And then we know that now using gradient descent algorithm, we are simply iterating the weight starting from to the to reach a local minima, to reach a local minimum point where you get the minimum error, and that gives you a classifier which is a kind of a low error classifier. Error function can be also modified, like no, you can consider that no, this is a quadratic. Instead of just simply summing up the positive terms, you can sum all the quadratic terms, and then error becomes smooth. And it can be also no, it has some advantages, some disadvantages. Smooth error has a smooth trajectory of in the gradient space also. But the thing is that no, in near local minima, it may be it may be a bit flat, so it may not reach exactly the local minima. It will be stuck at some vicinity, or it will be very slow near the minima, and you may not be able to reach there. So these are the issues when you say these things, but your convergence would be smoother and faster. And the other kind of scenario is that, which I have started by showing this diagram, that let us consider a bit more stringent condition. That means push this hyperplane more towards the positive half by an amount. Say this equation then this equation will be represented, say, by W transpose Y equals B. Then can you tell me what is this amount in that case? What should be the shift towards that direction? Which means, what is the distance of origin to this hyperplane? The same, say. So what should be the distance of origin with respect to this hyperplane? Anyone? Say this function I can write this function as, say, Fy equals W transpose Y minus B. Is it clear? This function I can write it like this. So when Fy equals 0 means all the points are lying on that hyperplane. So what is the distance of origin from this hyperplane? What do? You put the value of y as origin, like, and then the denominator should be the norm of W, isn't it? That means this distance would be, if I put the value of origin here, that means this value would be 0. Okay, this would be 0. So F origin, if I write origin vector like this, is minus B. So this should be minus B by norm of right vector. Okay, is it clear? Anyway, let me proceed in that case. Let me clear this diagram. So, so this is I was talking about. It is W transpose, or I should take W transpose X equals B. Actually, we can say also Y, because in our space, if I converted this data, then this is the shift. So there we define error. When we define error, we define the deviations from this value, from value V. So that means, given any W, what is the deviation? So if I take the scalar product, if I take this, so I can take some error like this. I have already shown you earlier in our earlier slide that I can take an error W transpose. Let me use Y here because we will be dealing with normalized data. So W transpose B, this whole square. Okay, this is the error, and they are normalized by the amount of the, otherwise it will be dominated by the long vectors. That means y which are at a very farther end, it will be dominated by that. So you are normalizing this. You are normalizing this by the norm, and this is your error. This is your error, which are to be minimized. And we have seen that, no, what should be the gradient? Anyone can tell me what should be the gradient? What should be the gradient vector? I may use half of such factor. Yeah, tell me.
If we take, then it will W transpose Y minus B into Y by norm of Y.
Very good. You are right. So W transpose Y minus B into Y. Sorry, I'm a bit, it's difficult to draw with the mouse here. And then you are having this. Yeah, I think that is fine, because no, this half and 2 gets. So you can see that this is the form, and of course no, you should sum them. That means for all the samples you are doing it for all y in your data. Here you may not require to check whether they are negative, positive, because as you understand that this error nicely takes care of. Oh no, you have to consider that. Sorry. So y should be misclassified sample. That means the y is such that W transpose Y is less than B. I'm sorry. You have to consider only those samples which are misclassified. So which means W transpose Y, those Y which are less than B. Is it clear now? Okay. So that is your I mean, this is the actually error definition itself. Y is it should be Y is such that W transpose Y is less than B. All misclassified Y with respect to this definition, this definition. So I hope this is clear, that how we can define error function and how we can compute gradient. So gradient here is a gradient vector, and a W is a vector in that space, parameter space, and bar or point you can say. So you should move in the opposite direction of the gradient. So you should move along minus grad JW and with certain step size, say eta into minus grad JW. Now, one of the interesting fact that has been written here, that we'll be soon discussing, that the support vector machines and the concept of support vector machines come from this kind of linear, finding out a hyperplane which will separate two classes when they are linearly separable. Of course, no, there are again generalization of that concept, but it starts with that, and we call them linear support vector machines, in particular when the form is linear, as in the function form linear. So linear support vector machine is nothing but a special case of linear discriminant function, and which optimizes this, or maximizes, I should say, this margin of separation between two linearly separable data points of classes. So we'll have this definition, concrete mathematical definitions later on. So we'll see that. So the batch relaxation algorithm, that what we discussed in the previous class, if I summarize them once again, it goes like this, that in the parameter space, you are initializing it with certain, some weight value. So which I'm denoting it here by W naught superscript is 0 there, as you can see. And we have to iterate. That means we have to move along the opposite direction of the gradient. You have to move along that. So that directions can be found in this way, that first you find out the set of misclassified samples, then you compute the gradient, and this is the gradient, as you have already mentioned. This is the gradient you can see. And here, of course, gradient is weighted by the square of the norm. I just mentioned norm there. It should be, I mean, that is what is used here. It is, instead of that, it is square of the norm. And you can update W, and this is the update rule, and you go on doing these things, still you converge. That means your differences of the components of these weight vectors, they are marginal, they are small. Now there is one interesting fact is that this algorithm, it can be modified even always updating weight with a single observation instead of a batch. As you can see, that flexibility is there. What should be the size of the batch? You have that flexibility. Now at the trivial case, if you consider the batch size consists of only one sample itself. Earlier the batch is the whole training set, but no, you can divide it into different batch sizes and you can do these operations, and you can go on doing these things operations. So in a very marginal case, it would be the single sample case, and then you can write this algorithm just for every sample. If you find it is misclassifying, immediately you compute the corresponding weight vector, direction of the weight vector, where it should move, and you update the weight vector. So that is what we are doing. Immediately we are updating, considering the ith sample itself, and we just go on doing these things for every sample in turn. You should see that now all the samples are taken in turn, and it will be go on iterating using the same sample over and over again with your when its cycle, when it's turn in that cycle comes. Every iteration, you can say, consists of updations with single samples of the whole training data set. At every step you are updating, and so we can call it as epoch. Also sometimes those terms are there. So when we stop when there is a very little change in update of the equation. Sorry, the weight vectors. So now let us discuss the. Now we are ready to discuss about support vector machine. As we can see that we have already discussed that what we are intending to do here, we are trying to get that hyperplane which should provide me optimal separation between two classes. Now, as I just mentioned, it's a linear discriminant classifier, and one of the interesting principle that this particular classifier uses, and Vapnik is the inventor of this support vector machine in 60s, in fact, invented, and there is another scientist whose name is I forgot. And so the idea is that to never solve a more complex problem as a first step before the actual problem, which means suppose I consider the class boundaries in this context. Now it is sufficient to look at, I mean, when you are considering the problem of classification, it is sufficient to look at the class boundaries. If you can identify the samples in the class boundaries, then that determines the shape of the corresponding discriminant function in that boundary. So that is what it says, that sufficient to compute class boundaries without computing class distributions. That is very important aspect, that we may not require to compute the whole distribution, and which means we are trying to compute some sort of outliers that where the separating those x having these I should say this probability would be low, probability of x okay, boundary separating those x having low px. So outlier in the sense that you may consider some of those samples which are rarely occurring, so you may leave them. So these are the two things which one should consider here. And here the support vector machine you will see later on with the mathematical treatment analysis that we'll present here, we'll discuss, we'll see there, that actually these class boundaries can be represented as a combination of these input samples itself. So as if they are the resultants. We have seen already that when you compute the gradient is computed as the resultant of the directions of the input samples which are misclassified, and you are moving along that directions. Now, interesting to note that the weight vector can be represented itself for this kind of linear function. That weight vector can be also considered as the resultant of the training samples which are lying in the class boundaries. So that itself is defining the class boundary and the linear function. That is very interesting observation, a very exciting observation, I should say. And these vectors, that's why they are called support vectors. So let us go into a more formal definitions of the problem and then the formal treatment of the problem. This is an optimization problem, as I mentioned. So let us understand the formulation of this optimization problem for the support vector machine. So we consider a training data set which like 2-class problem training data set, as you can see here. And again the superscript T, it just denotes the instances. And there are, in a training data set, you have these two information. One is the input feature vector X, another one its label R. And in a 2-class problem, we are considering these labels are here +1 and -1. That is also considered in support vector machine cases also. We'll see that implication of this label itself, because in analytical treatment, the label value plays a role while optimizing the objective function. So this is the definition. The feature vector is an element of a d-dimensional real space, and the label could be either +1 or -1. So now you have two scenarios that we are considering. So we are modifying this linear discriminant functions policy. Earlier, the policy was that if I simply compute the linear function, then if it is positive, then it belongs to say +1, and then if it is negative, it belongs to -1. But now my policy with the training data set, once again, let me tell you, it is with respect to the training data set, is that it should be a function. If it is in the positive half, then the functional value should be greater than +1, just not greater than 0. And also, if it is in the negative half, then the functional value should be less than -1, not just 0. So there is a sufficient margin between these two. There is a sufficient margin between these two. That is the definition of the problem. So it's a problem definition. Okay. So with respect to that, we are trying to find out the hyperplane, which will maximizing, say it will satisfy this constraint and also maximize the distances between these two boundaries, class boundaries. Now this can be written nicely in a single constraint, in a single form of a constraint. It's not single constraint. You can see that it's a multiple constraints, because if there are n samples, there would be n constraints with respect to this. And but the form of this constraint can be written in this form, right? So simply you multiply the label with the functional value, and that value should be always greater than equal to positive value, +1. Okay. Any question? Do you agree? So that is the reason I told that class labels has to be +1 and -1. This is one reason that you can convert it nicely, this problem, into these constraints are in an uniform form. So you don't have to put a conditional things, whether it is class 1 or -1. The class level information itself is included into the computation of constraint in the mathematical form. And it's a harder constraint than if the class boundary is a hyperplane passing through origin, that you understand. So you have it leaves a margin between two zones of classes. So let us try to understand margin between classes. You can see a very simple example here, where you have a class with 3 samples. They are denoted by these triangles, and a class with rectangular objects, 2 samples. So just diagrammatically, if I consider a kind of hyperplane, this is a direction, and that is touching. These are the boundary samples. This could be one example that in that directions, if I take an hyperplane in that direction, this would be the margin. This would be the margin of separation between two classes. So we would like to get that hyperplane, which will give me that directions of hyperplane, which will give me this separation maximum. So the equation, of course, here it is restricted by this form that W transpose X plus W naught minus 1 equals 0. The role of this plus 1 and minus 1, it comes in this form. And where the other discriminant function is W transpose X plus W naught plus 1 equals 0. So for the training sample, no, you are considering these two discriminant functions. And when we compute the distance between these two hyperplane, these are the equation of the hyperplane. So what should be the distance between these two hyperplane? Can anybody tell me what should be this distance? So what should be the distance from distance of, say, origin from this hyperplane? So what is the distance, this distance? What should be this? We just discussed in the previous case itself. What should be this distance?
W naught minus 1 by norm of W.
Yeah, you are right. So this distance is W naught minus 1 by norm of W. Okay. Is it clear? Anyone has any doubt? Is it clear? What about this distance? Say for this hyperplane, I am also computing the distance from origin. What about this distance?
W naught plus 1 by norm of W.
Right. W naught plus 1 by norm of W. So what is the distance of separation?
2 units.
2 by
Norm of W.
Yeah, just not 2. So distance of separation would be, so if I say this is the distance of separation, that would be 2 by norm of W. Is it clear, everyone? So what is your objective? What is your objective? Your objective is to maximize. Your objective is to maximize this separation, right? Maximize this separation subject to satisfying these constraints. Subject to satisfying these constraints of placement of the objects. I mean, those mathematical form, that level R, product of that R and this discriminant function W transpose X plus W naught minus 1, that should be R into W transpose X plus W naught minus 1, that should be equal to, that should be greater than 1, or rather R into W transpose X plus W naught should be, say, greater than 1, and when it is plus 1 and minus 1 for certain input samples. Okay, so that is the constraint for every input samples. So it's a constraint optimization. So minimization of this function means what? You can say also it is also maximization problem, because 1 by inverse, instead of that, I can say that we are maximizing this denominator. So which means the function is that we need to maximize the norm of W, and in fact I can write it in this form that give me a smooth function. Instead of simply W norm, I will be writing half of square of the norm. The same. We'll be maximizing this. That's the quadratic form, subject to the constraints what I mentioned. So this is the optimization problem. So I'll be summarizing them, of course. So let me just clear this screen. So as I was mentioning, so these are the two boundary hyperplanes with respect to a particular direction, and so this is the separation of these two hyperplanes, and then you have to maximize the margin. To maximize the margin, sorry, I just said the opposite thing. To maximize the margin, you have to minimize the denominator. Yes, sorry, I said the opposite thing. So finally, this is your optimization problem. That, as I was mentioning, instead of just minimizing the norm of W, we are minimizing the square of W, the square of the norm. Of course, we are dividing by 2 because that factor, as you have already discussed, helps you in eliminating the factor 2 in the expression of the corresponding gradient.
So why are you taking square of the norm?
It is basically the function would be more smooth. Usually that is the way these distances are taken. Okay. And this is the constraint what I was mentioning, that all these constraints should be satisfied. Okay. Is it clear?
Yes, sir.
Okay. So let me proceed then. So we'll be discussing about this optimization problem now. So as you can see that this is a constraint optimization problem, and we need to minimize this particular function, square of the norm of the weight divided by 2, and the constraints are expressed in this way. That means all the samples should be placed in its corresponding site of the hyperplane, as we have mentioned in the positive and negative, but they are expressed in this uniform form. So one of the things you can see that actually this, you have asked that why I have made square. Actually, one of the things is that it gives you the functional as a convex function. I should have mentioned that it's a quadratic function, then it becomes a convex. Also, it is a convex function. It's a quadratic and it's a convex function. Quadratic function is a convex function of W in the parameter space. So it becomes a convex optimization problem. This is one reason to choose this square. So how to make it an
answer? That way norm is also, sorry.
Norm, no, norm is a square root is there. Square root is not this.
Yes, but norm is also a convex function, right?
Norm, there is a square root operation. Just check that part. See, if I don't take norm, the square of norm means that square root operation is getting. So I hope you understand what I'm trying to say. Say you take a vector, say two-dimensional vector W1 and W2. So these are the two components. So how do you express the norm?
Root over W1 square plus W2 square.
Right. Root over W1 square plus. Now see, this y equal to say root x, y is the function. Is it a convex function? If I say y equal to x square, right? Y equal to x square, how does it look? Y equal to x square, it would be like this, right? And what about y equal to root x? That means it is the other way, x equal to y square. So you have this issue, right? So that's why you take this square. Because if you have convex function, then there exists only one global minima.
Oh, okay.
There is no question of getting stuck into a local minima.
Local minima, yes.
Yeah, and also convergence, etc. becomes there are good properties of convergence. Now that's why people would like to get this kind of optimization problem, if it is possible, into the convex optimization problem cases. Of course, it is not purely convex optimization; it's a constraint convex optimization. right? So there is a catch. So you cannot simply use that gradient descent approach, etc., to get the local minimum. I hope this is clear now. Okay, so let me just remove this. So how do you solve this kind of constraint optimization problem? What is the approach you follow?
Lagrangian.
Exactly. Use Lagrangian multipliers. Is it a familiar form to you? It's a minimization problem.
In PCA and
yeah, in PCA also you have used it. You see that these constraints, individual constraints, are summed up into this Lagrangian form because they are all additive. So how many free variables are there, free parameters are there in this unconstrained problem? Can you tell me? Suppose it's a d-dimensional space and there are n samples. That's a good question. No? Say you have a X is a d-dimensional space, right? Or d-dimensional space, and T, that means the number of samples, is capital N. It has been shown here also, capital N. Okay. So what are the number of parameters in the unconstrained problem? Will it take so much of time?
So n plus d plus 1.
That's exactly. So I hope others have understood. So you can see that this is a parameter W, W naught, and Lagrange multiplier. So these are the parameters, and if you count them, it will come to that number, what he has mentioned, n plus d plus 1. So these are Lagrange multipliers. And no, I can simplify this expression into this form. There is a subscript P, which is written here. Now, those who have studied mathematics at particular optimization, they immediately understand the meaning of this subscript. Actually, this kind of problem can be solved using certain primal dual conversions of the optimization problem. This kind of constraint convex optimization problem. So we'll just come to those formulation. So we call it primary objective functions because it's the direct one, and there could be an equivalent objective function where we will be we'll be simply maximize. So this is a minimization. So in this case, the function is minimization with respect to W. You can see that though there are parameters alpha, etc., but the function is with respect to W. Minimization is with respect to W. And there we will be considering in the other way that the function would be maximization with respect to. So in this case, actually minimization with respect to W and maximized with respect to Lagrange multipliers. And in the other form, we can make a dual form, which is that we can maximize it with respect to Lagrange multipliers, subject to that gradient with respect to W and W naught should be 0. It looks at the other way. So in the previous case, it was also like that, minimization with respect to W, and then you also subject to the gradient of all those alpha should be satisfy that condition. But the thing is that if I take the gradient of with respect to this multiplier, you can see they are simply giving back me those conditions only. If I take the gradient with respect to individual parameters, Lagrange multiplier, I'm simply getting that conditions only. So I'm not really moving ahead with. I'm not going to get any new as a perspective of this computation. It's the same computation. So I'll be minimizing with respect to W, and I'm lining up with the same constraint. So the other trick is that why don't you consider the other way, that you consider the problem where you will be maximizing with respect to this multiplier, and you impose the constraint of gradient with respect to parameters of W as 0. Then you convert it back to the other kind of equation. So you just replace W, those conditions. So let us see that how we can write these equations there. So which means that now if I take the gradient with respect to W, we get these are the two conditions. One, you can see that it can be expressed as W equal to sum of alpha R X. It's very interesting, right? So W is expressed as the function of alpha and X with respect to when this condition satisfied. That is the, I should say, the relationship. I should say relationships of W and alpha at the optimal point. And similarly, there is also constraint on alpha and R, which is the class level at the optimal point, which comes from these conditions of minimization with respect to, the gradient with respect to W naught should be 0. So these are the two constraints that again, or two relations that again we can substitute in this particular functional form, and we get the dual functional form, which needs to be optimized. As you can see, we have eliminated all W's. We can eliminate all W's from this expression and replace them by as a function of only alpha, R, and X, where you have to maximize with respect to alpha. So that is the dual conversion. So once again, if I show you that conversion, this is the dual conversion. It is just one step, which shows that you can write first alpha LD in this form. You are replacing, you are replacing all W with respect to this. Now you are just simply, simplifying this expression, which means this has become now W, and this is 0 already. You can see if you look at the two equations above the one. Let me also point out, see this one, this equation, and this equation. Okay, so from this you are applying this equation here, and you are applying this equation here. So you get this, and then again further reduction is possible. Further reduction is possible. So which give you this. Fine. Further reduction is also possible. What reduction? That W can be completely eliminated, isn't it? How? W can be eliminated from this expression, and expression should be functions of alphas only. Because you know that levels and training data feature vectors, they are already given data. They are specified. So only variables will be this Lagrange multipliers in that case. Agree? So let us see that form itself. Once again, I am writing this. Oh, there is a constraint that alpha t should be greater than or equal to 0. That constraint is there for that maximization. Still, that constraint is there. So you expand W from this condition, and you get this particular, because you are maximizing it. Expand this condition. So the idea, you should maximize this function with respect to alpha values. Of course, this has to be satisfied. This alpha t is greater than or equal to 0, and sum of alpha t or t should be equal to 0. Now it can be shown that most of them will be 0, and it can be shown. Actually, it's a quadratic optimization problem, because it's a quadratic function. Quadratic function of alphas. It's a quadratic function of alphas, and then you can apply quadratic optimization technique. There is no closed form solution. Apply quadratic optimization technique to arrive at a solution, and there is a algorithm where you have, because there are n number of alpha parameters, so the time complexity and space complexity becomes this. So apply quadratic optimization technique, and these are the characteristics. You will find most of the alpha will be 0. In fact, those alpha which are lying on the boundary, class boundaries only, they will be non-zero, and they form the support vectors. And that's how the weight is a linear combination of input samples. That means you get your solution in this form. Only those alpha which is contributing here, and they are all positive, those alpha will be defining this term, and it's a linear combination. So you can see that samples which are meant for class 1, it is contributing as a positive contributions, and in the class which are in the, that is in the negative contribution. So both the classes are involved. Samples of both the classes are involved in the boundaries, and they finally derive this particular direction and W. And how do you get W naught? Because no, you can get W, which means now you can find out that the samples which are in the class boundaries, that was information also you are getting. You are not only getting W, you are also getting alpha non-zero, means you are identifying those samples which are lying on the class boundary, which means if I perform W transpose X plus W naught, what should be its value? W transpose X plus W naught, depending upon the class, it should be either +1 or -1. Is it clear? For all the samples in that boundary, they should satisfy this. So any sample you take and you get W naught. So finally, this is the expression, but no, from the statistical point of view, there would be some, it may not be exactly, all W naught may not be same for all the samples in the boundary. So you can take the average of them. Any doubt? Any question? Okay. But the interesting part is that, see, all these exercises we have done for training samples. When we are considering testing, there we are not using that +1 -1 principle. We are, for our convenience, because now we have given a separation, and also this problem solution is meant for only for linearly separable classes, not for overlapping classes. Linearly non-separable classes are not, we have not discussed yet. We'll discuss tomorrow. So all these cases, all these discussion is relevant for linearly separable classes. So when you test, you can simply test that whether the sign is positive or negative. You take the dot product of W, or you compute W transpose X plus W naught. And if the value is greater than 0, then it is belonging to class 1. If the value is less than 0, it is belonging to -1. So there only the sign of discriminant value is considered, and margin is not enforced. Only support vectors decide class boundaries. Other samples do not influence the classifier. That also we see. Right. So maybe today we should give a stop.